Thank you. So after all these nice talks about what we can do with high contrast imaging, now we are going to be back to a bit of more instrumentation aspects. So I'm going to talk about how water vapor in the Earth's atmosphere can affect the performance of high contrast imaging. And most of the things I will show today are thanks to the contribution of several people. And I would like especially to dedicate this talk to the memory of Matt Wilson, who tragically passed away last month. So now let's move on with the water vapor thing. So what I'm going to talk about today is how the inhomogeneous distribution of water vapor in the Earth's atmosphere can affect the performance of high contrast imaging in the mid-infrared. And so the phenomenon that I will be talking about is this one, where above the LT aperture, which is synthesized here by this parabola, you can see that the amount of water vapor, so the column density of water vapor, can be different above different parts of the pupil. And that, of course, leads to wavefront distortions. And because water vapor is chromatic, especially in the mid-infrared, the correction that you will get at the K-band from your adaptive optic system will not be the right one to feed the instrument at a longer wavelength. And so we can quantify this phenomenon by looking at the refractive index of water vapor in dry air. And we can consider that a molecule of water vapor displaces an equivalent molecule of dry air when it moves inside or outside the optical path. And that's what we call water displacing air. This is a concept that was introduced 20 years ago by Jeff Meissner and company. So if we make the difference between the normalized refractive indices of water vapor and dry air, we get something like this, where the chromaticity in the infrared is mostly due to the water vapor. And what you see is that compared to the K-band, which is here shown with the gray line, the refractive index is different at L-band and even more at N-band. And if you have 1 mole per square meter of column density of water vapor in the atmosphere, you will get an additional delay of 0.5 femtoseconds at L compared to K, an additional delay of 6 femtoseconds at N compared to K. And of course, if that is time variable, that creates aberrations. So now the question is how much aberrations we will get. And for that, we can use recent measurements obtained at Fresnel with the VLT interferometer, using the fringe tracker of gravity at K-band, which provides a few measurements across the K-band. We can look at the chromaticity of the fringes and predict what is the amount of water vapor and what, well, most of this chromaticity is due to the presence of water vapor. And so we can predict the amount of water vapor and its variability in the atmosphere based on this data. And actually, we can check that these predictions are good by looking at the position of the fringes while observing with METIS at N-band or L-band at the same time as gravity at the K-band. And this is a work that has been done by Philippe Berriot from the METIS consortium, predicting the position of the fringes at N-band based on gravity. So the predictions are in red, and measuring them with METIS, showing a good consistency between the predictions and the measurements. And so from these phase measurements, you can deduce the amount of differential water vapor between the apertures in your interferometer, and you can produce time series that I will be using to try to constrain the amount of wavefront distortions on ELT scale. And so you see that here, the measurements have been taken with a short configuration of the auxiliary telescopes, which happen to have the same scale as the ELT aperture, so about 30 meters. So these are the results we got with the gravity METIS experiment. Depending on the amount of water vapor, the precipitable water vapor in the atmosphere, so going from dry to humid atmosphere at parallel on parallel standards, you see that the amount of variability in the differential column density of water vapor increases, although not linearly with PWV. We still have to understand exactly how that scales together. And these measurements can be compared with things that had been done 20 to 30 years ago, based mostly on radio observations. showing that the amount that we get at Paranal is on par with what was obtained in other observatories, although somewhat lower, mostly because the baselines were longer and the timescales were also longer. Actually, the only experiment that was using these kind of baselines and the single time scale is the one performed by Jeff Meissner 20 years ago, giving similar amounts of differential water vapor, although these experiments were quite crude at these times and give only approximate numbers. So now we have a better understanding of these. So now that we know the amount of differential water vapor condensity, we can, well, first check whether this follows a Kolmogorov statistics as expected. And actually, this might not be fully the case. So in the worst conditions, the worst cases, I saw the power law to be quite close to the -1/8 that we expect from Kolmogorov statistics. But in the best conditions, which are the ones that leads to this 1 to 2 10 to the -19 centimeter per centimeter square differential water vapor condensity, it's more like -1 to -4/3, which is not what we expect from Kolmogorov. So we still have to understand this a bit better to see whether this is the norm and what are the consequences on the rest of the things that I will show, because for today, I will assume that the fluctuations are following Kolmogorov-von Karman statistics. So how much additional nuisance do we get from that? So first, let's try to convert these units into something that is more understandable. So this condensity fluctuations actually corresponds to a little less than 1 mole per square meter of condensity, and which can be translated into a variation of about 6 micrometer of PWV. So that's typically 1/1000th of the amount of PWV you get along the column. And if you convert that into a delay using these normalized refractive indices I already gave before, you get additional delay of about 0.2 femtoseconds at L band and 2 femtoseconds at N band, which correspond to this kind of path lengths, which are not negligible compared to what you will get from adaptive optic systems. So now these are local delays measured on the ELT base, the VLT baselines. Now, how do we scale that to the ELT? Actually, we can do that pretty easily because, as I said, the VLTI baselines are on the same scale as the ELT pupil. So we can generate a sequence of phase screens on the ELT pupil and then just define these 4 apertures and try to make sure that the variability of the wavefront on this aperture matches what we observe with gravity or METIS. And this is what we have done. So we have generated these sequences. We have plotted the pistons between the 4 apertures. So there are 6 baselines, and we have just make sure that the variability of these pistons match what we have actually observed with gravity and METIS. And once we do that, this is the kind of things we get. So here on the left, this is the phase screens that we expect from the adaptive optics. So these are the residuals from the adaptive optic system, which give about 140 nanometers RMS of wavefront error. In the middle, you add the contribution of water vapor at L band, and on the right, you add the contribution of water vapor at the N band. And so you see that at L band, the additional contribution is quite minor, but N band, water vapor is largely dominating the overall wavefront quality budget. So with an additional wavefront error of about 300 nanometers RMS on top of the AO residuals.
You have 2 minutes left.
Yes. So in terms of stride ratio, the effect is not big. Actually, at L band, the stride ratio barely changes. At N band, you go from 99 point something to about 95% of strail, which is not a big deal, I would say, for most of the imaging programs. But if you go for higher contrast imaging, this has a significant effect. So these plots, they show what you expect to be the sensitivity in terms of contrast as a function of the angular separation at L band and at N band. In black, these are the predictions for purely AO limited performance. And in blue, this is what you get when you add the contribution of water vapor. Orange is what you get when you just remove the tip tilt from the AO phase screens. And so you see that at L band, the degradation is not big, but at N band, you get a serious hit in performance when adding the effect of water vapor. And so there are ways to mitigate that. And the way that we plan to use with METIS is to use the science camera as an additional wavefront sensor, which can sense both the non-compass aberrations, but also the chromatic effect of water vapor seeing. So adaptive optics will only give you what it sees, but there are things that are unseen by the AO system that we'll need to correct using the actual science camera at the right wavelength. So the science images will be fed back to the AO system for focal plane wavefront sensing at a frequency of typically 1 Hertz. And we'll be using 2 algorithms, one for the pointing errors, another one for the higher order modes, up to about 100 Zernike modes, which give us a well-corrected zone of about 5 lambda over d around the center. And so this is what we expect to be able to achieve after these corrections are implemented. So you still see the same black and blue lines. Now the orange line is what happens when we correct for the tip tilt, and actually operating our pointing algorithm at 1 Hertz basically kills most of the tip tilt. But this is not enough, especially at N band, where you need to continue correcting for higher order modes if you want to recover something that is close or at least close enough to what you expect from the pure AO limited performances, although you cannot really get there. And so these are just correction at different frequencies. If we could go faster, this is what we would get, but probably we will be around the green curve there. So these are my conclusions. So we investigate the variability of the wavefront in the mini-infrared due to the water vapor at Paranal. And the conclusion is that the N-band image quality at ELT scale is dominated by water vapor turbulence. For most programs, you won't really care because the image quality is good, but when you go for high contrast imaging, you have to care about that. And the take-home message is that taking advantage of the low PWV events will be even more important than ever, because we already thought that this is important for low background conditions, but on top of that, this will probably need it if you want to dig as deep as you can in terms of high contrast imaging. So, thank you.
Thank you very much, Olivier, for this super important talk, and a bit scary as well to see how it affects the N band. Oh, I see there is already a first raised hand, so you can go ahead, Bruno.
Yes, thank you. Thank you, Olivier, for your nice talk that you already presented us in the frame of METIS. Do you expect a difference between the L-short wavelength below 3.3 micron and above? As you know, below 3.3 micron, we are more affected by telluric line. Well, not necessarily by water vapor line, but CO2, I think, and methane as well may affect this wavelength regime. So do you expect difference below 3.3 micron and above 3.3 micron of the L band? And if so, maybe it would be good to use METIS medium spectral resolution data, which show more detail and information about telluric line that in low spectral resolution data.
Yeah, so I must admit I have not looked at other species than just water vapor. Also because it's much harder to predict the effect of other species. As you said, there are some wavelengths where they can be seen, but for instance, from the gravity French tracker, I would not be able to predict any other the contribution of any other species. That being said, if you have phase measurements with METIS, I mean, dispersed across the L band, I think it would be interesting to make this kind of analysis and see whether other minor species can be also harmful there.
Yeah, yes, for both instruments, there are ongoing work by Alexis, as you may know, to CO2 better take into account and correct for telluric line effect below 3.3 micron, but it's probably two different regimes of the L band that may appear below 3.3 and above. There might be two domains to consider, and well, probably there are also specific filter in METIS that could allow to select whenever side of the band, but it's probably nice to refine your study by looking at medium or high spectral resolution data. Would be interesting for both METIS and METIS, I would say. Thank you.
Okay, thank you.
I'm running out of time, so if Denise, you can be quite quick in your question, and Eric, do you mind writing your question on Slack instead? Sorry about it.
I had a few questions, so I will just ask one and the rest on Slack. On the slide where you show the Kolmogorov comparison, there is a huge peak at high frequency. I was wondering what is that?
Yeah, so let me reshare my screen. Sorry, what's that? Yeah, so these peaks, I mean, they are purely instrumental effects, I guess. I haven't an idea what this is exactly about, but I mean, looking at the frequency at which these appear, I mean, I guess these are either hiccups in the French tracker or some other instrumental effects. But yeah,
sorry to intervene. I think it's the 48 Hertz peak of the secondary mirror of the VL, maybe of the VLT.
Yeah, it seems to be at like 700 Hertz here.
Oh, you're right. Sorry. Yeah.
Yeah. So this is more
that high frequency.
Yeah. Yeah. Me neither. I don't exactly know what it is. We should have a discussion about that with the gravity and METIS teams, I guess, and the ISO.